Okay, so we're going to do, call it an introduction to quadratics. So what I'm just going to do is give you some different views of this function called a quadratic. So we're used to this, y equals x or y equals mx plus b, okay? These are both linear functions. We've seen these before. We'll jump over on our page here and we'll give an example of y equals x. Gives us, oh, I'm not in a great spot on this graph here. Let me zoom out a bit. There we go. It gives us this nice line. And then y equals mx plus b. Give me some sliders here and I can move it all around. There's our slope. Our m changes the slope of something. And our b changes the y-intercept up and down. Okay, so we have a little bit of familiarity with this. Let's see if I can get it back close to being parallel. Oh yeah, not bad. Oh, that wasn't that great. Okay, that's a linear function. We're going to move on to another one here. Y equals x squared. And when I say or, there's actually quite a few different versions we use. I'm going to use this one first. Y is equal to ax minus h squared plus k. It's a lot more variables involved in this one. The first thing I'm going to do is I want to draw similarities between these. The one you see here that I'm about to highlight in yellow, oh, I thought that was going to be yellow. There we go. The one I'm going to highlight in yellow here, that's a version of a linear and a quadratic, and I should give this a title actually. Call this quadratic. These are known as parent functions. And a parent function is like the simplest form of that. These are technically called functions. It's the simplest form of that function you can create. So no extraneous details, no extra coefficients or constants involved. It's like the bare bones version of it. Now, I will tell you this. Technically, this x is to the power of 1. We just don't ever write it in. We don't write it in because it's redundant. It doesn't change anything. But the power of 2 here does, so we do write it in, okay? But I want you to notice that really in the parent function, that's the only difference. This is to the power of 1, y equals x power of 1. This one is y equals x to the power of 2. But what you're going to know, so that's algebraically not a lot of difference between the parent functions. But I do want you to notice this. I'll turn this one off. There is quite a difference graphically between the parent functions. And if you notice that green one, that's a very different graph than our purple line. So our green line here is a quadratic, it's called. It has almost like a U-shaped pattern. So that parent function is very different. And that's going to be important for us, okay? In our linear function, we had slope, and we have y-intercept, okay? Now, this is actually called the slope-intercept form. There's an actual name for that form. You can actually represent linear equations many different ways. This one here is called vertex form, which that word may not mean much to you, except maybe in geometry. But what I want to show you on a graph is there's something specifically called the vertex. And the vertex here, okay, the vertex is the lowest point. So down here, that's the vertex of this equation, okay? This form gives us a lot of information about the vertex. In fact, the h, it'll tell us what the x value of the vertex is. And the k will show us the y value of the vertex. And then the a is a little different. A has to do with how stretched or compressed something is. Okay, we'll call it a stretch or compression. Okay, and what I'm going to do for the next bit is I'm just going to show you how we can transform this function, this quadratic one, okay? So we'll jump back into our graph here. I'm going to eliminate our other pieces. Okay, so we have those two parent functions, which I'm actually going to turn off at the moment. And I'm just going to say y is equal to ax minus h squared plus k. And it's going to ask me for a whole bunch of sliders. So you'll notice this one's a little shifted off. Right now, its vertex is at 1, 1. Okay, so in other words, the h is 1 and the k is 1. I'm actually going to move it to 0 and 0 so that it's on the origin. There we go. Okay, and what I want to show you about this is I want to show you that if we increase the k value, that actually shifts the entire function upwards. And if we drop it, it shifts the whole thing downwards. Okay? There we go. So that gives us the 0. If we shift the h value, that actually moves it left and right. Now there's a trick about this is that, let's get you to a whole number here. h6, when I plug into this equation, is actually -6. It'll look like because there's a negative in front of it. But you'll notice that the x value is positive. So the h has this like inversion effect, that the operator is the opposite direction that we would think on a number line. Okay? So if we keep moving that h and we go to the left here, it goes down to the left. Okay? And we'll get it back at the origin. Ooh, I'm getting close. And finally, stretches and compressions. As the a value increases, think of it like an elastic band getting pulled upwards. It gets thinner and thinner. And then as it gets closer to 1, it gets pretty wide. Between 0 and 1 gets really wide. And then when it's negative, it flips the other way. Okay? So you'll notice it gets extremely wide, and then it jumps up and around again. And we usually leave the a value at about 1. That one's a half, which is nice. Okay? But that is the general idea of linear and quadratic equations. The only other major thing I would talk about here is there's something called first and second differences. So in math, we use a lot of different tools. This is our algebra. I think I spelled that wrong. Algebra? I don't remember how to spell it. We have algebra, we have our graphs, and then we have tables, which are a really nice way of looking at things too. And tables allow us to plug in different values. Whoops. Okay. What we're going to do in a table is we get x values and we plug in y, find y values from there. So a common table might start at like -2, -1, 0, 1, and 2. And we would plug that into this equation, x squared, to find out what our y values are. So for instance, -2 squared is actually 4. -1 squared is 1. 0 squared is 0. 1 squared is 1. And 2 squared is 4. And that's how we essentially go about plotting these things. We are at -2 and 4, -1 and 1, 0, 0, 1 and 1, and 4. And that gives us this quadratic look to it. Okay? If we were to try to find the y for a linear function, and we plugged it into the parent function, it would just be -2, -1, 0, 1, 2. And that's how we get that linear or straight relationship when we connect all these dots. So tables can also give us a lot of information too. What's nice about Desmos here is we can very easily convert. I'll turn that off for now. And we're going to convert these. I believe I can change that. I'll put that one into a table and this one into a table so we can see the differences between them. And notice that it actually gives us some major points across the linear equation, the one in purple. And then our green one, it also gives us some major points here. And these are actually considered like the major points of a quadratic, which are good to know. Okay? So that's kind of an introduction and comparison between linear and quadratic functions.